Now, last graphing example of the day. This one a little different, a little more well-behaved derivative this time. However, this time we're going to have vertical asymptotes, oblique asymptotes. We're going to talk about how to recognize all those things. So here we go. Now, similar steps here. And by the end of here, I want to talk about that acronym that we sometimes use to remember all these steps that have to go in here. So I'll do that right at the end. I'll remember to do that right at the end. So the very first thing is, I think you're going to help yourself out a lot if we just go ahead and factor this the best we can. That's going to be nice. Oops, forgot the equal sign in there again. F at x equals, there's only one little bit of factoring to do here, a little common factoring here in the numerator. And so sometimes you'll want to use the factored form and sometimes you'll want to use the not factored form. It just depends on what you're up to. So let's go through those steps. First step, look for domain issues. And in this case, we're looking for denominators and square roots. And you're like, square roots? We haven't seen much of square roots. I know. That's tomorrow's video, so we'll talk about square roots a little bit more. For now, denominators. And so we can't have x minus 4 come out to be 0, so we can't have x equal to 4. That's the big thing there. And we're going to talk about what that means in just a second. So we'll get to that when we get down to asymptotes. Intercepts. So for y-intercept, set x equal to 0, so I get y equals, well, that numerator is going to be 0 minus 0, that's 0. The denominator is 0 minus 4, that's negative 4. So 0 over negative 4, y-intercept of 0. Now, x-intercepts. And that's where I'm going to use the factored version of this. I need that numerator to come out to be 0 for x-intercepts. That means I'll get a 0 on the top, so I get x equals 0 or x equals 3. So I get this second one, and you might get more than that depending on the function and what degree that numerator is. Okay, now asymptotes. First, let's check out the vertical one. Here, because that denominator had a 0 and it wasn't in common with the numerator. That was the little but that we had back in advanced functions. We said if it's in common with the numerator, then it's actually a whole, and we can find that limit. And so it's not a limit off to infinity. It's actually just a spot where the function approaches but never quite gets to it, and that makes a whole in the graph. So I mentioned the holes right there, but this one isn't a whole because it's not a factor in common with the numerator. So all I get is an asymptote, a vertical asymptote at x equal to 4. I forgot already what it was. X equals 4. Okay, now the next kind of asymptotes is we look at this degree comparison between the numerator and the denominator. And so our rules, and let me review the rules again. If the denominator had the higher degree, we'd have a horizontal asymptote at y equals 0. If the degrees of the numerator and denominator were equal, what we'd have is a horizontal asymptote at y equal the ratio of the leading coefficients. And you can get to that with that 1 over the biggest x power trick if you've seen that as well, but I'm just quoting the rules here. And finally, you could get there if the degree in the numerator is 1 more than the degree of the denominator, then you need to do long division to find that oblique asymptote. So here, I've got to go take that x minus 4 and divide it into this x squared minus 3x. And if you remember, for long division, anything that's missing, we got to put a 0 in there as a placeholder. So in this case, it's a 0 at the end there. And then this long division, I got to put an x there, x squared minus 4x, and subtract. I get x, bring down the 0, I get a 1 there. I get x minus 4, and I get plus 4. Remainder sort of doesn't mean anything in this. All I'm looking for is that quotient. And so what I get is an oblique asymptote at y equals x plus 1. That quotient there indicates where that oblique asymptote, where this function is going to approach as it gets off the sides of the page. Now, I'll show that to you in a minute, how to graph with oblique asymptotes. Now, next, intervals of increase and decrease. And for me, I like to go back to the non-factored version of this. Often that's a little easier to deal with when we're doing derivatives. So, f prime at x, derivative of the top times the bottom, minus derivative of the bottom times the top, all over the bottom squared. Lots of simplification to do here. F prime at x, multiply out these brackets carefully, 2x squared minus 8x minus 3x plus 12 minus x squared plus 3x. So I get f prime at x equals, let's see, 2x squared, I got an x squared minus 11x plus 3x is minus 8x, and then a plus 12. Now, is there any reason these things should come out and nicely factor down after all this? No, but we use lots of examples that do, just so we can use our factoring skills. If it didn't factor, then we would go to the quadratic formula. If it was a degree 3 that wouldn't factor, boy, we'd need some other specialized methods, but we'll worry about those later. For now, we make a lot of them that either factor or do the quadratic formula nicely. Now, for critical numbers, set f prime at x equal to 0. So I get x equals 2 or x equals 6. But I also get x equals 4, because 4 is where this derivative does not exist. So I need that for my chart. So don't miss out on that anytime this thing doesn't exist, we want that in our chart as well. So for our chart, and I think I got enough room for it here. Here's this parts of my chart: x less than 2, between 2 and 4, between 4 and 6, and greater than 6. And you know what? I'm just going to do this chart a little bit faster to sort of encourage you that these charts don't have to take forever as you get a little bit better at them. You don't have to be overly experienced to really speed up this process here. So x less than 2, I'm just going to think in my head 0. And if I got 0 in my head, I got negative, negative, positive, which means positive in there. And so I'm trying to inspire you that with the proper thinking, these charts don't have to take long. So between 2 and 4, I'm going to think of the number 3. And so when I subtract 2, I get positive, then negative. On the bottom, it's squared, so it's still positive. I get a negative in there. So I slowed that one down just a little bit. I'll slow this one down even more if I'm going too fast. X equals 5 is a good test value between 4 and 6. 5 minus 2 is positive. 5 minus 6 is negative. And 5 minus 4 squared is positive. So that's interesting that that went negative, negative there. And then x greater than 6, say 10, it's going to be positive, positive, positive. That gets positive, so I get increasing, decreasing, decreasing, increasing. So I didn't get as many max mins as I might have thought I would have. I got a max at 2 comma something and a min at 6 comma something. Now, when I sub that 2 back into the original function, I go back up and I think I get a 1. And when I get a 6, I get a 9. So those come out to pretty nice values. Now, one thing that might help you, and you might be curious, why is this thing going decreasing, decreasing? And I really suggest when you get these things, I'm going to highlight it here, this other critical number, this number that where the derivative doesn't exist, that instead of drawing on your chart a straight line, a little cheat, not a cheat, a little shortcut, a little reminder. I sometimes actually write that as an asymptote right on my chart, and it reminds me what the heck is going on there, and that I don't get confused about what's happening, that this is decreasing, and the reason that is because, the reason it happens to be in this case is because I have a vertical asymptote there. So that's good to mark on your chart there. Helps for later thinking. Okay, so that's the single derivative, all done. So now I'm going to go after the double derivative. So now concavity. And for concavity, I need the double derivative. But first, I'm just going to copy down that single derivative from up here. The non-factored version is often the easier one to work with. So that was x squared minus 8x plus 12. And the denominator was already factored. I'm not going to bother multiplying it out. You could, but I'm going to leave it the way it is. X minus 4 squared. Especially when it's degree 2. Doesn't come out too bad here. So a little bit of a mess here for the double derivative. So here I go, double derivative. Derivative of the top times the bottom. Minus the derivative of the bottom, little chain rule here. 2 bracket x minus 4. Derivative of the inside is just 1, so I don't really need that there. And then times the bottom. What a mess I'm getting here. All over the bottom squared. And then my advice here is to tidy up any monomials you get here. And I don't have any monomials here. But I am going to do one little thing here. You don't have to do things like this, and I didn't do it in the last video, but I want to do it here to remind you that it's in that half step, sometimes it's good to pull out any monomial common factors. That can really make a big difference in what you're doing if you pull out any monomial common factors that you have there. So once I did that, I'm looking for common factors to the first term and the second term. I see a 2, I see an x minus 4, and I think that's all I see, and then I'm going to open a square bracket. That's my little move I like doing. You'll see some textbooks do that. And it really helps to stay organized when you've opened that square bracket so you can really see what's left inside the brackets. So I pulled a 2 and an x minus 4 out of that first piece. Oh, I made a copying error there. That was still squared there on that line up there. So when I common factor 2 and x minus 4, I've still got x minus 4 squared left in that bracket, and in this bracket I've still got x squared minus 8x plus 12, and this is all over x minus 4 squared. And like what often happens here, oh, that's not squared on the bottom. I'm just catching that now. Just erase that. I actually said it when I did it earlier, but I didn't write it. Let me just rewind a little bit here and go, okay, that was derivative of the, right up here was derivative of the top times the bottom minus derivative of the bottom times the top, all over the bottom squared. So that's a power of 4 down there. And so now, like what often happens is that x minus 4 sort of cancels. That common factor goes with the denominator. So what's going to be in the denominator is an x minus 3. Sorry, x minus 3. An x minus 4. But now it's down to cubed. And in the brackets, okay, I got to expand out that x minus 4, so I'll go x minus 4 times x minus 4, do that expansion, x squared minus 8x plus 16, and then this is subtract x squared plus 8x minus 12. And so after I tidy that all up, the inside brackets comes down to x squared minus x squared, oh, that's gone, negative 8x plus 8x, oh, that's gone. 16 minus 12, 4. Oh, this really tidied up nicely. How nice is this? F double prime equals 8 over x minus 4 cubed. How nice is that? So when I do 4 points of inflection, set f double prime x equal to 0, I get no x values. But I still have to build my chart, because I still get x equals 4 as that where it doesn't exist, and that's got to go on the chart. But it does make my chart pretty easy to build here now. I just need x less than 4, x greater than 4, and I only got to worry about f double prime at x equals, what, 8 over x minus 4 cubed. So less than 4, I'm going to use a 0 as my value. That's x less than 4. And when I put that into the double derivative, I get positive over negative, because 0 minus 4 is negative. But when I cube it, I still get a negative. So this is negative. So this is concave down. And the next greater than 4, I'm going to use like a 10. And so I get 8, which is positive in the numerator. And then 10 minus 4 is like 6 cubed. That's like positive as well. So this is concave up. So I do get a... Now, I'm going to make a mistake here on purpose, okay, folks? I'm going to guide you through a mistake that you'll do sometimes. Is you'll go, oh, so I do get a point of inflection at 4, comma, and then you go back to your original function, you sub it in, and you get 4, and you sub it in here, and you go x squared, 16 minus 4 over 0, and your calculator says undefined, and you go, undefined? How can that be undefined? And you go back here, and you go, oh, that's the vertical asymptote. That x equals 4. And now you like my trick a little bit better. When you build these charts here, is to draw the asymptote right on there, because it can cause confusion if you don't do that. And so this is not a point of inflection. There's no points of inflection here because it's a vertical asymptote, and that's why the concavity changed. And if you're like, I don't get it, how can the concavity change it there? Well, okay, I'm going to show that to you on the graph that I'm going to do, because I'm going to tie all this stuff together, and hopefully it'll clarify everything that's going on here. So for me, I go right back to the beginning. I say, okay, domain x can't equal 4. What kind of domain issue was that? That was a vertical asymptote at x equals 4. I'm going to try and draw that in there. Ooh, choose a light color that we can't see all that well, like this. I just want it subtly on there so I know that that's a vertical asymptote. Now, vertical asymptotes are stop signs. You can't go through them, not like horizontals or obliques. Verticals are like domain issues. The graph can't go through here. Okay, so next thing I got to put on my graph, that was the domain issues. And then the x and y intercept. There was an x-intercept and a y-intercept of 0. And I'm going to go with black this time because I really want to be able to see the oblique when I get to it. So, and so x-intercepts, 0, and there was another one at 3, weirdly. Isn't that interesting? That 0 and 3, so that tells me a lot about what's happening here. This function is either going to go up and then down to the asymptote, or down and then up to the asymptote. I guess I'm going to need some more information. Oh, the oblique asymptote, y equals x plus 1. Now, it's hard to draw obliques on here without making a big, sloppy mess. So sometimes what I do is I first draw this oblique asymptote in a light color. Say I'm going to use green here. For you, a really light pencil. And I draw the oblique asymptote here, y equals x plus 1, and it will be sort of like this. You see I'm drawing it all the way out here. And now it's right in the way and maybe causing confusion as to what it actually means. And so one thing sometimes I do is I draw this thing all the way out like that, this y equals x plus 1, and then I get my eraser out and I just erase a bunch of it. You know, say, okay, well, I'm really not too worried about this oblique asymptote, because oblique asymptotes aren't stop signs. You can draw right through them if you need to for what you're doing in the graph. The important thing is, as the graph goes out to the edges, it approaches that oblique asymptote. So if that wasn't made clear before, now's the time to really understand that obliques are just end behavior. So I really just like them at the end there. If you've got your own way of handling that, that's fine as well. Okay, so, and now I got to get back to my regular pen and draw on the other thing. So I put on the oblique, I put on the vertical asymptote. What was next here? Oh, max mins. I found a max at 2, 1, and that's huge information. That really tells me what's going to go on here. And then a minimum at 6, 9. So interesting. 1, 2, 3, 4, 5, 6, 2, 4, 6, 8, 9. Right about there. I just want to count that one more time. 2, 4, 6, 8, 9, 6, 9. Yes, very interesting little piece of the puzzle. Now, so increasing to that max, then decreasing into the asymptote, and then decreasing, increasing. And actually, what's interesting is I can get a really good drawing of this graph just from what I've seen there. But the concavity really brings it home. If you look at the concavity, we've got to be concave down before we get to 4. So I got to be concave down. See how I do here if I can get these through these points. So there's concave down, and that really tells me how to approach this thing, what shape it's going to be. And then over here, concave up. This part was a bit of a mystery in advanced functions. We just sort of went with it. But if this is going to be concave up, then it has to approach this asymptote. and approach this asymptote. You see how the concavity is just like the, the cherry on top of the sundae here. It really brings the shape into this thing so you know exactly what this thing looks like, and you're not mystery as far as what's happening over here on the right side of that vertical asymptote. Now, different teachers, different profs are different. Some like to label everything. So I'll agree and I'll write it all on there. But I'm going to tell you my own personal feelings on some of this. I'm going to write in the same color I did here. I like this other color here. I'm going to write y equals x plus 1, that oblique asymptote. And I'm definitely going to write in another color here so you can see it. I definitely like having the vertical asymptote written on there. But the other points are all whole numbers and they go through exact points. So sometimes I find labeling points that are obviously on points like that just makes things messier and doesn't add any clarity to the whole situation. But some teachers and profs like it, so let's get in the habit of doing it so we don't get ourselves in any kind of sort of danger later. Now, I'm worried about that max pin because I said 2, 1, and I drew it through 2, 2, and I'm just noticing that now. So let me just see if it's going to let me tidy that up with the eraser here. No, it's not. So I'm going to be a little tricky here, and my screen's froze for just a minute here, so I'm hoping that's going to come back in just a second. Ooh. Small eraser. Ooh, small eraser. Oh, there we go. Now I can tidy that up a little bit. I just noticed that when I went to label it, so I guess that's a good thing I went back to label it, because when I went to label it 2, 1, it wasn't through 2, 1. And then right in there, so if you want to fit these in there, 3, 0, I can write it over there, just draw a little arrow, and then here this one was 6, 9. So it's nice to have those labels on there to see everything that's going on there. Okay, that's the last curve sketching example today. There's lots of homework ones to try. Check out these steps as you go, and have a great day.